Good evening, everyone. Hi. Can you hear me? And am I amplified? Yes. Am I amplified?
Yes, you're amped up.
Okay, I'm amped up. Exactly right. Great, because you never know. It's funny sound down here compared to up there. So first of all, let me say welcome and thank you for those of you who braved the fires. You are probably aware, and you probably saw if you're just coming in, a new fire just right over there by the LA River. And for those who are not, who might be watching on our stream, the LA River is right over there. So I think the 5 and the 134 may be shutting down. There are all kinds of things going on. Another day, another fire. I know we're all very tired of this. So I just want to thank you who were able to get here, for being here this evening. And tonight we will talk a little bit about the fires, but we will hopefully help you forget about them with so many other stories from the cosmos that we are very excited to share with you tonight. So let me begin by introducing myself. I'm Dr. Laura Danley. I'm our host for All Space Considered. And with me, as always, Dr. David Reitzel and Patrick So. And we're your correspondents to bring you the latest and greatest in space and astronomy news. Okay, thank you. Well, that wasn't a hint. We need one of those applause things that's, off camera, and then, oh, look at that, spontaneous applause. And when to laugh really uproariously at our jokes, right? No, we don't have those kinds of signs. But I'm just going to put this here because it gets cold down here. So this is All Space Considered. How many of you are here for the first time? Never been to All Space Considered before? That's remarkable and wonderful. How many of you have been here more than once before? Okay, fantastic. And for those of you who are here for the first time, how many of you are here because a friend brought you? And how many of you are here because you saw it in a newspaper, a physical newspaper, like you opened the morning paper and you said, look at that. Okay, that was a big no. And how many of you saw it on a website, any website? Okay, so really it's all the word-of-mouth friend thing by and large, but there are still some who just came here because you saw it, and we're very happy to have you here. A couple quick announcements before we get started. If you need to leave because of an urgent need to leave, please go out the back doors, the ones you came in. That direction is actually a closet, and you will then have to turn right around and walk past everybody, and it's always, kind of embarrassing. And that way is an emergency exit, and it goes through this kind of crazy maze with many choices of which door number 1, door number 2 to go through. If there were to be an emergency, we would guide you out. Only some of those doors work, because you can always get out through the emergency, but it's a little confusing. But if there were to be an emergency, we would take you out that way. So please do go out the back. Also, you can keep your cell phones on because there is no cell signal in here. So to that end, we recommend that you turn off your cell phones because they'll spend the evening roaming, looking for signal, and it'll run down your battery, and then at the end of the evening, when you want to take a picture, you want to call a ride share or something like that, you will have no battery and you will be sad. So go ahead and turn it off. It's not going to, if you have an alarm, it might go off, but no calls are going to come in, and you're not going to be able to text anybody or anything like that. Okay, lastly, how many of you are members of Friends of the Observatory? I love your hand was up before I even really... Thank you, Friends of the Observatory. Friends of the Observatory is our sister 501c3 fundraising membership organization that underwrites so many of our programs, most notably our 5th grade school field trip program. So if you like the future and you would like us to have a future with well-educated people who understand science, the time to get them is when they're in 5th grade and coming to Griffith Observatory for a school field trip program. So please consider becoming a member. If you don't want to become a member, you don't. It's a little. I think it's $50 for the lowest membership level. You can always just drop an Abe or a Jackson or somebody in one of the little collection bins, because Friends of the Observatory appreciates all the donations that our friends can offer. And then lastly, how many of you are tax-paying citizens of the city of Los Angeles? We like to thank you because not a lot of people know that Griffith Observatory is owned and operated by the city of Los Angeles. This is a municipal observatory. How many cities have that? Not a lot. So we are civil servants, and therefore, again, if there were to be a problem, we would guide you safely to the right place. But it's your tax dollars that support Griffith Observatory and its staff. So we are very, very grateful to you. Okay, I think that's it with all that preview stuff. I think there are lots of prizes tonight. Bill, do you want to tell us what's up?
I'll get to the calendars last. Now, welcome everybody. So if you have been here before, you know we play this game during the course of the evening. We were playing various cuts of music as you entered, and each one of those pieces of music is related thematically or by some sort of word association or something to one of the stories that you'll hear tonight. When that story comes up in order, it's quite all right to shout out the name of the song that you heard or the piece of music or some identifying thing, that Beatles song or whatever. And if you do that, and if you're the first to do it, you win a prize. Now, the prizes, we've really stepped up our game here. We have all kinds of prizes that came from our wonderful guest from the Chandra X-ray Observatory. And we have, I think most of you probably were offered a bookmark of some sort on your way in. We have more of those, but we also have pens and pins. We have to pronounce those separately. Pens, which commemorate the 20th anniversary of that wonderful observatory, and two different kinds of pin, two different designs that also commemorate the same thing, and they're really wonderful. I'd also like to point out that we're always encouraging young people to think about STEM careers. STEM, of course, is science, technology, engineering, and math. And we have some special information from NASA on, this is a sheet that highlights a bunch of women who work specifically in high energy physics, studying the high energy universe, as our guests will speak of tonight. And we also have some sheets that are one-sheets on just women in STEM, and they go to websites, and there are all kinds of fun projects and things there. And we encourage all young people to think about it, but particularly girls these days. So. We also have how to talk to a spacecraft in binary code, in case you want to do that at some point. Lastly, I'm just going to say, just because everybody looks forward to this part, we have calendars. We have calendars that are all completely out of date. We have a calendar here for the Mars rovers, which you'll hear about tonight. And they go back to 2013 and 2014, but I would like to point out that the calendars from 2013 can be used again in 2019, which is now. 2014, I know it's getting late for now. 2019 will be good again in 2030. I know we're November 1st, so you probably don't want to start a new 2019 calendar. 2014 will be good again in 2025, and that all of that works for all of us. We actually have one that somebody left us to give away that is Zeiss constellation figures. Zeiss meaning, it doesn't mean our telescope, does it? I'm not sure. I haven't opened it, so you can explore it yourself. But it's a perfectly good calendar for 2019, which means you can use it again in 2030. We also have mission stickers, so there's all kinds of fun stuff related to the talk you'll hear tonight. And thank you, and have a wonderful show.
Thank you, Bill. And for the record, I'm not accepting that Beatles song. If you can't name a Beatles song, you don't get a prize. I'm sorry. I draw the line at that. Okay. On with the show. So tonight is November 1st. Happy Halloween. Happy All Saints Day, everybody. I hope yesterday was spooky and that today is sacred for all of you. And this is the first Friday of November. We have All Space Considered on the first Friday of every month. So, well, almost every. Spoiler, we're not going to do January 3rd because holidays, out of town, blah, blah, blah. But we have a special program 2 weeks later, and we'll tell you all about it in a little while. But usually first Friday of every month. And so as I mentioned, today is November 1st, and I love this title. Well, and the Nobel Prize goes to, so we'll tell you about that. I love Borisov, Borizon, Purple Haze and All My Frame. I'm not going to go through all these titles, even though they're all wonderful. We have speaking of wonderful, special guest Pat Slane from Chandra, has already been mentioned, and we will tell you more about him when he's going to join us. And then a few other stories, Apollo 12 anniversary coming up, pretty picks and break as we always do. I also like Royal Air Force says, what to Griffith Observatory?
Tally ho.
Yes, there you go, tally ho. Um, so we're in the second half going to start with some cosmology. We don't cover cosmology enough in this show. And I love cosmology, and you're going to love it too if you don't already. And so, in fact, we're going to have a fair bit of cosmology, the big stuff, the universe as a whole, that we'll be talking about tonight. So there are a number of those. News from Mars, news from ancient Earth that we'll talk a little bit about. And then we'll finish up the evening with some discussion of things going on in the human exploration programs, plural, because it isn't just NASA anymore, around the world, taking us to space, us and our machines and our robots and eventually people. And then finally, we will look back at the career and life of Alexei Leonov, who was a Soviet cosmonaut who passed away this past month. And remarkable individual. We'll tell you about it a little bit later. Okay, so on with the stories. We begin with the Nobel Prize. Nobel Prize in Physics was awarded just a couple of weeks ago to these three individuals who share it. Jim Peebles, who, as this says, for his theoretical discoveries in cosmology, and Michael Mayor and Didier Queloz. I don't actually know how to pronounce his name.
I think that's right.
Okay, I'll go with that, if anyone has a better idea, for their work on finding the first extrasolar planet around the sun.
On the prize?
Eyes on the prize, excellent. Yes, a prize to that gentleman. I'm sorry I can't give you a Nobel Prize. And you know, I forgot to say hello and welcome to our guests who are on our stream. Hope you are home safe. I guess you are in your jammies with your tea or whatever it is you're enjoying at home. So thank you for joining us remotely. All right, so I'm going to begin by talking a little bit about Jim Peebles. Jim, Jim, to everybody who knows him, a lovely individual, born in Manitoba. He's very careful to say he's not from Winnipeg. He's actually from the Francophone sister city, actually a suburb of the Francophone sister city, St. Boniface, in Manitoba. And came to Princeton University, where he spent his entire career after graduating, his undergraduate at University of Manitoba, and then went to Princeton and stayed there forever, where he is still. The citation in for the prize says he took on the cosmos with its billions of galaxies and galaxy clusters. His theoretical framework, developed over 2 decades, is the foundation of our modern understanding of the universe's history from the Big Bang to the present day. Another way to say it is he is the father of modern cosmology. And I had the tremendous joy this past week. My poor colleagues and coworkers are so sick of hearing me talk about how much fun I had listening to lectures from Jim Peebles, because he's probably one of the best lecturers. It's just a total joy. But I saw an interview with him with Sandy Faber, a professor with whom you worked, and she referred to him as the inventor of modern cosmology, and I'm going to go with that because he has his fingerprint in everything in the story of modern cosmology. So to that end, I am going to give you a little bit of a background, little mini 4-minute college course on cosmology, because to understand what's so remarkable about him, you kind of need to know some of the basic pillars of modern cosmology and the Big Bang Theory. So for this work, he won a Nobel Prize, and this picture is taken from the press conference that Princeton had for him. And as it looks, as you can see, even just from his picture there, he is quite modest, quite lovely, and a colleague that is loved by all. So, the history of the universe in just a few minutes begins like this, where the universe is filled with a foam of radiation and matter that through gravity coalesces into something that we refer to as the cosmic web, for obvious reasons. Gravity pulls things together in clumps that are connected by strands, and you can see that all these little clumps all start, again through gravity, collecting together, making big galaxies bigger and medium-sized galaxies big, medium-sized, and gravity just wins and pulls everything together in this wonderful structure that's referred to as the cosmic web. So it's a story of how that happened, and even before that, how the universe, how even that matter came into existence through what we now know as the Big Bang, or we call the Big Bang. The Big Bang has three main observational pillars. The first is the expansion of the universe. That dates back to Hubble and Humason and Slipher, if you want to be precise, who were observers who developed, who found that everything seems to be moving away from us, and the things that are farthest away from us are moving fastest away from us. It's what's referred to as universal expansion. The whole universe, oh gosh, I was about to sing that song. Okay. The whole universe was in a hot, dense state. And that really, it's true. That song's very accurate. Because if you run the clock backward, as this picture does, you can see that as things were compressed, they were hotter, and at the very beginning, the implication here is that it was a very hot birth. The other implication is that there is a birth, that there's a start. It's not a steady state universe, but that there is a point in time where the universe started expanding. And that term, that time, point in time, is referred to as the Big Bang. So again, because it's hot, as you know, hot things expand and cool. So reverse the slide. They're hot when they're all smushed together. It must have been hot, and I liked putting must have because I'm going to put it a few more times. Because it was hot, there must have been fusion, nuclear reactions, smashing nuclei together. And this little picture on the left shows all these very light elements, helium, deuterium, lithium, beryllium, and so forth, that as the temperature cooled, the cooking, the nuclear fusion cooked up all of these light elements that are referred to now as primordial nucleosynthesis. And if you do the math and you do the model, you can predict and then compare to observation how much lithium, deuterium, hydrogen, helium, so forth is in the universe. The really first very quantitative development of that was done by none other than Jim Peebles. Okay, so that was one of the pieces that he worked on. Another piece related to the hot Big Bang is it must have been glowing very brightly in the early universe. And we now know that we can see that leftover glow everywhere in the sky in what is referred to as the cosmic microwave background radiation. So those three kind of ovals, which represent a representation of the entire sky, show sort of the history of what we've learned about the cosmic microwave background radiation. First, it comes from all over the sky, and if you just have sort of a crude instrument like the Bell Labs guys did in the 1960s, you just see the same radiation coming from all over the sky. But if you can get higher resolution observations, as they had with COBE in the early 1990s and with WMAP in the early 2000s, and Planck, another European mission, did the same experiment at much higher resolution and sensitivity, you see that it has teeny tiny, and by teeny tiny I mean like 1 part in 10 to the 5th, fluctuations in the density. It's not perfectly smooth, it's a little bumpy. And those fluctuations turn out to be super important, and I'll come back to that in a second. So here's another thing that you can calculate, which is if you've got the clock ticking and the universe expanding and things are cooling, you can calculate the thermal history of the universe. And, oh, there he is, Jim Peebles. There's a pattern here, and I hope you're seeing it, with Robert Dicke and Wilkinson is from the WMAP, Wilkinson Microwave Anisotropy Probe. If you don't know what I'm talking about, don't worry about it. But this is their paper in 1965. You can see May 7th on cosmic black body radiation. And you can also see where they say they're so grateful to Drs. Penzias and Wilson of Bell Labs. And if you know the story of the Big Bang, those names might be familiar to you. If on that same page, in that same journal, you look at the next paper, there's the references, and oh, here's this thing, a measurement of excess antenna temperature. That is the name of the paper that announced the observational existence of the cosmic microwave background. It doesn't sound all glamorous. It's not like clickbait headlines you'd have today. You can imagine what they do with that today with clickbait, but no, a measurement of excess antenna temperature, and that is by Penzias and Wilson. So the two papers were back to back. They collaborated, they coordinated. Actually, it's a fantastic story. I don't have time to tell you now, but the Princeton people had worked out the theoretical framework, meaning Jim Peebles, who was the theorist among that group, Dickie Peebles, Roland Wilkinson, he had worked out the theoretical framework, and the others who were experimentalists were building the apparatus, looking for it. And meanwhile, right down the road at Bell Labs, Penzias and Wilson were wondering, what the heck is this excess glow that we can't get rid of in our data? And so someone suggested they speak to one another, and it's like, that's what I've been looking for. Oh, that explains our excess. It's the Big Bang. It's the relic radiation from the Big Bang. So Penzias and Wilson got the Nobel Prize, about a decade ago, or maybe a little longer. And so at long last, Jim Peebles, representing the Princeton group, did as well. So here is the history of the universe 13.7 billion years ago, where you had your hot moment of creation from which everything expanded. I'm not going to go through the details of inflation, but there's a moment, and without going into any detail, when it cools enough that the radiation and the matter is just finally transparent enough that the radiation can fly free from the matter. And locked in to that moment, so it's like a signpost or a peg in the story where you know and can look at what the distribution of the density was at what they refer to as the decoupling or of the cosmic microwave background radiation. And those fluctuations, that little lumpy, bumpy stuff that's right in that is very, very important, holds some very important information. So in fact, I will just say it's so important that there is now a plushie, and in fact a pillow. You can get the WMAP or the Planck. And as I was saying to you guys earlier, if anybody wants to give me a Christmas present, I would really like one of those plushies. That's a hint. Usually I say it's not a hint, that's a hint. So, but if you look at the angular separations of the lumps and bumps, the bright and dark mottled sky in this cosmic microwave background radiation, and you plot up how much of the sky is covered in bumps separated by this much versus bumps separated by that much versus bumps separated by this much, you get a graph that looks like this. Look at the points. Those are data, and then the models fit the points to see if we can explain the amount, sort of the nature of the lumpy bumpiness. If it were a different time or a different physics, you might imagine that the separation of those lumps might be greater, or they might be smaller, or there might be lots of little ones and not so many big ones, or in other words, the models, and now again we come back to Jim Peebles, who is the one who did this quantitatively to try to figure out what is the nature of that lumpy, bumpy pattern, and what does it tell us about the state of the universe, 13.5 billion years ago. And so David is going to be talking about a new and improved versions of these measurements. This is from WMAP. It's about an 18-year-old map. But you can see that there is clearly information there. And here's a more cleaned up one from Planck, same idea. And, but there's more, because not only is the microwave lumpy and bumpy, but the universe is lumpy and bumpy in the form of galaxies and galaxy clusters. So you can compare the lumpy bumpiness then to the lumpy bumpiness now. And again, it tells you've got another post. You need to have the laws of physics get you from here to here in an internally self-consistent way. Again, Jim Peebles did the mathematical development of that theory. And I guess that one has, I don't know, I have it in there twice, my apologies. And so there are two papers, one in 1982 and 1984, large-scale background temperature and mass fluctuations due to scale invariant primeval perturbations, again, a non-clickbaity title. But it is, he describes it through the development of something called cold dark matter. And you've probably heard of dark matter. There were some other people working on it at the same time, but this very elegant paper tied it all together and gave a mathematical framework to explain what he could explain through cold dark matter. Now, he couldn't explain everything, and so 2 years later had a different paper in which he had what's referred to as lambda cold dark matter. And lambda refers to the cosmological constant, which is something that we now relate to dark energy, the expansion, that energy that expands is making the expansion of the universe accelerate. If you've don't know what I'm talking about, it's crazy because the universe is expanding and you would expect that all the stuff inside, the gravity inside, would make it shrink back down, just like throwing a ball up into the air and gravity pulls it back down. No, the universe is not only expanding, it's accelerating an expansion. So what magic force is doing that? That's what lambda is and does. And there's a lot of, or probably, this is work, now we're right at the frontier. Another outcome of this, because now you had to explain, and through those lumps and bumps, and through the development of structure from the from the cosmic microwave background radiation to the present day galaxy distribution, to fit that, to make that work, one of the results is that us, atoms, are less than 5% of the universe. And most of the universe is made up of dark matter and dark energy. That's the outcome of trying to get those galaxies that we see today to be the result of those fluctuations, of density that we saw right back after the Big Bang. So when you hear that story, like, we're not even the main stuff around, that's sort of where that comes from. And guess who did that? Jim Peoples, right? Okay, so you can see what I'm getting at. So there's our story of the universe. Jim had his hand in galaxy formation structure, lambda cold dark matter, the mathematical calculation of the nucleosynthesis of the Big Bang nucleosynthesis, and of the cosmic microwave background radiation. And actually, he began his career at Princeton doing gravitational physics. He didn't go there to do gravitational physics. He wanted to do particle physics, but got so drawn in by Professor Robert Dicke and his Friday night parties, soirees on gravitational physics, that he joined that group, and then that's what he's done ever since. So he is throughout the whole development, and what he's really credited for is turning it from kind of some ideas into a self-consistent, coherent, mathematical framework that makes predictions, turns it into, and from which those predictions can be observed. Like science, making it a real science, because up to that point, there had been pieces, but it hadn't been all tied together. So there are so many people, and this is just a handful, and there are many I haven't, but Jim Peoples went across all of those disciplines. And to top it off, he is one of the world's most wonderful people that you'll ever meet. Kind, humble, generous as a mentor and a teacher. I knew him and have been at meetings with him and learned from him. And so I'm going to conclude with just a few videos of him that will give you a sense of his passion for discovery and his passion for what he does. And then there's one final little coda that I just loved so much I had to share.
So where's all the antimatter?
Not part of this discussion. So I'm going to move forward with this.
I find it amazing always to consider that nature operates by rules that we can discover. In cosmology, we're invited to apply that same theory extrapolated to scales that are about 10 to the 15 times larger. Spectacular. Why in the world should you assume that the same physics would apply on those scales as in the solar system? But in 1984, when I put together that theory, I was very unhappy with the fact that it grabbed a lot of attention. Why are you concentrating on this particular theory? I could make a dozen others up that would fit the data equally well. This was the simplest possibility, but by no means the only one. But the evidence kept appearing. It was quite a joyride.
I love that. Lifelong career of a joyride. And he's in a room full of physicists, so I love that you're laughing over I could fit the data with any of a number of theories, because anyway, that's very much. Anyway.
We can be very sure that theory isn't the final answer. And we can be very sure that as we discover new aspects of the expanding and evolving universe, we will be startled and amazed once again. I hope you guys hurry up to make those discoveries so I can enjoy them.
And then lastly, this was maybe one of the favorite moments I've ever seen in a news conference like this.
Joe Connors with CBS. Do you have any exciting plans for the prize money?
Much of it will go to charity. Some of it will go to charity. Some will go to our children. I must say, I owe a lot to the University of Manitoba, and a chunk will go to it.
So that's Jim Peebles. If you didn't know who he was, I'm really honored to get the opportunity to share with you who he is and has been, because he's such a remarkable man. So the other winners, David?
Yeah, the other winners, Michel Mayor on the left, and at the University of Geneva, Switzerland, along with Didier Queloz, they shared the other half of it because they discovered 55 Pegasus B, or Pegasi B. That seems weird. I always call it Pegasus B. Anyway, it was the first exoplanet, in other words, a planet going around another star, that was found to be orbiting a sun-like star. So each of them gets, in our mind, half of a Nobel Prize because they have to split it. Although in my mind, I was wondering, should it be a quarter of a Nobel Prize because they're getting half of it? Anyway. Pegasus, by the way, is a constellation. 55 Pegasus B is the 55th brightest star in Pegasus, so you're not going to see it in a map like this. You're not going to see it from here, but it is up in our sky in November, so if you get to a dark site, you could go out and see Pegasus. I think it's amusing that it shares stars with Andromeda, so those constellations making things simple. It was found using the radial velocity method. So as the planet was orbiting the star, it puts a little tug on it. The planet's gravity tugs on the star, just like the star's gravity tugs on the planet, equally on each other. While the planet makes a big circle, the star makes a little wobble. So sometimes the star's moving towards us, sometimes away from us, and we can pick that up with using the Doppler shift. We can watch the spectral line shift in the spectrum of the star. So they did that, they had data, they verified it, and sure enough, it was a real planet going around a real star.
A very nice connection, very nice surprise.
So very nice surprise, nice connection. Here he is on his computer when he heard the news about it, the cafeteria at the airport. All the messages flooding in, congratulating him about his Nobel Prize.
It came up so much as a surprise to me. It's just an unbelievable and fantastic news for this field of research, which is now growing so fast.
So, and again, surprised to get this. Now, why are they so surprised? Well, a lot of folks felt that exoplanets haven't quite risen to the level of cosmology and learning about, the fundamental roots of where our universe comes from. But in reality, this planet sort of kicked off the discovery of many, many more. And we can see that here in this graph that goes by. They found one, that one in '89, by the way, was found to be wrong, just this year. 51 peg there, although I'm confused by this. 55, 51. I thought it was 51 peg.
51 peg.
It was labeled 55.
Oh, it's 51.
Yeah, that's what I thought. Anyway, I was reading it. Anyhow, you can see the numbers are just going nuts, and we had to change the scale on the graph there as that more and more are discovered each year. So to this date, there are 4,084 exoplanets that have been discovered. So that's crazy. And this is the first one around a sun-like star. Now, what do we mean by a sun-like star? Well, 51 Pegasi is only 11% more massive than our sun, 23% larger, so on order of very much like our sun. It's on the main sequence. The exoplanet itself is very, very hot, about 1,000 degrees Celsius, 1,800 degrees Fahrenheit. That's because it orbits its star every 4 days. It's only 5/100ths of an AU away from its star, so that's about 20 times closer to the star than we are. Yeah, it's 50 light years away from Earth, but it's what's known as a hot Jupiter. It was one of the first hot Jupiters that was found. It kind of threw a wrench into our works of how we thought planets formed. We didn't think that should be there. People were thinking this might be the core of an evaporated who knows what. Well, now we know it's probably stable. Now that they've done models, it's just puffed up. So it's larger than Jupiter, even though it's only about half the mass of Jupiter. It's so hot that makes it expand and be sort of puffy. So quite an exciting discovery that's worthy of getting the Nobel Prize, considering this was the first planet around a star like the sun. And we call them exoplanets, of course, because it's around another one. So an exciting time to see the exoplanet research community get rewarded and to get this award. So fun times.
I was just thinking 55, I think, might be 55 Cancri, because there's a 55
There
Cancri.
is.
So I bet that got swapped in
They
something.
probably did somewhere.
Yeah.
The computer might have done it on its own, the troubles we were having earlier today. So, now speaking of other visitors from other, well, not other universes, but other solar systems, we have a visitor flying through our solar system right now. It's a comet that we think came from a different solar system, so it's coming in and visiting. Here's the discovery image of it. It's the fuzzy thing in the middle, looking a lot like a comet. Those long streaks are stars that were allowed to trail as the camera tracked the comet. You can see it here as it flies in. It's been named 2I for Interstellar, the second interstellar visitor, and Borisov was the man that discovered it. Here's where it is today, November 1st, kind of crossing the plane of the solar system just about. And as we continue on its journey, it'll head down and still get a little closer to the sun in December, so it's not even at its closest point, and then it's going to fly out. You can see here some information about it. The distance is in the top versus time, and then in the bottom is sort of brightness, and the brightness is going to peak after November 30th. So it'll be closest to the sun in December, and it'll be brightest in the sky in that time too. Although brightest still means about 17th magnitude for any of you astronomers out there, amateur astronomers. You need a pretty big telescope to see 17th magnitude, so this is not one you're going to run outside and see. The Hubble Space Telescope can pick it up, however. This is a Hubble image of it, and an animated Hubble image as it flies past those stars. Very cool. They have made some measurements on it. It has a color that's much like the color of other comets, the red arrows indicating where it would be in this distribution, and it's right in kind of the center part of the color of what comets have, so nothing too surprising. So far it seems kind of normal. Here's a spectrum of it, so if you take the light from the comet and break it into the rainbow and measure how much energy you're getting at each little wavelength, it looks kind of normal. It looks like a D-class comet, whatever that means. It's the first I'd ever heard of those. Here's another spectrum of it, very not super high signal to noise, meaning it isn't very smooth, but there are some of these wiggles that look like they're real. Perhaps that one is real, that bump is probably real. If we move ahead, some more spectra of Borisov still, and the bottom part is that CN emission. So that's carbon-nitrogen compounds have a whole forest of lines through this region, and they're common in comets. Here's a spectrum actually of, this was of comet 67P, the comet that was visited. So you can see that big CN spike that's in there. This is, again, common in comets. This is comet Hyakutake, came by in 1996. And again, you can see that CN spike and the C2, C3, C2. Anyway, these are just common comet spectra. And in fact, Borisov is looking very much like this. It's looking like a normal comet, even though it came from another star. So super cool.
Can I ask a quick
Yeah.
question? The one that a couple of years ago, the one that
Yeah.
Omeo? Yeah, that was its name. What was its spectrum? Did it have the CN or was it?
No, it wasn't outgassing.
Okay.
It seemed to be rocky or anyway. It was a weird object because it did change velocity as it exited the solar system. Yet, to the best of our ability, we saw no outgassing. And we should have if it were outgassing to the level to change its orbit. So it was a weird object, but yeah, so very strange. This one's behaving a little more normally, so if they'd all behaved like the other, could have been cool. Anyway, comets in our own solar system come from the Oort cloud or the Kuiper belt. This one was moving too fast to have fallen from those locations, so we know it didn't come from there. It had to have fallen from much further away. In fact, it passed by one of these stars. Let's see here, that one, Kruger 60, about 1 million years ago, and it flew quite close to it. It was a handful of light years away from it, and maybe it came from Kruger 60. It's possible, we're not sure, but some folks are saying it was very close to there in the past. So maybe that's the view of where it originated, the double stars there, as Borisov comes flying towards our solar system.
Okay, from out there to a little closer to home, Patrick, you want to tell us
Indeed.
about
So-
these beautiful sunsets?
Yeah, so if you enjoy, if you enjoy looking at sunrises or sunsets, you probably notice there's a little bit something odd about these sunsets, even a few months ago, I went out and took a picture of this beautiful sunset from the roof of the observatory in September. And you notice there's a purplish color above the main yellowish sunset. And there's a reason for that, and it all stems from a volcano located in Russia. There it is, its location. The volcano, next picture, is called Ryukyu volcano. And it hasn't erupted since 1924, but on June 22nd, it erupted, and it was observed by the International Space Station and 2 Earth-observing satellites. And here are some of the images after its eruption. Spewed up a lot of dust and gas and sulfur dioxide up into the stratosphere, about 43 to about 53,000 feet. And we go to the next slide. And the jet streams basically spread all of this ash and dust globally at that height. We can go to the next slide, and we can see some more of the initial eruption. And it formed basically, in the next diagram, a aerosol layer in the stratosphere. And the last time this happened was the big eruption in Mount Pinatubo in the Philippines. And you can see that ash layer in the stratosphere. This was taken by the space shuttle back in 1991. And we go to the last picture. I took this picture just a few days ago, and you can still see that purplish sunset. And the reason for that is that when blue light is scattered by particles in the atmosphere, and when you look towards the horizon, towards the direction of a sunset, all the blue light scattered away and leaving the red to come through. And these higher ash clouds do the same thing. So you have reddish light filtering through the ash cloud, playing against a deep blue sky. So the addition of red and blue gives you that purple, and hence these purple sunsets. They won't last because eventually all the aerosols will filter out of the atmosphere and you will get our normal sunsets. But go out, enjoy your sunsets, and take a few photographs. You can get some beautiful photographs while it lasts.
Thank you.
Can I ask, will that create any cooling effect globally?
I think it's very thin. I'm not sure how much cooling you can get from that.
Okay, so just to alert you to a headline you may have heard, we all love Saturn because isn't it pretty? But the big headline this month was that Saturn has 20 more moons than it originally had. We've got just one, but it's got all those to wrangle. So because it was so lovely, Brendan, I think, is back in the studio, in the theater, or in the booth, but he made this wonderful race. You can look at the years of how many moons have been discovered. And if we were betting, we could place bets on this, but you already know the outcome.
Circus rolling the balls.
Yeah. So. So if you placed your bets on Saturn, you win because Saturn now has a bunch of 20 new moons. Here's the Subaru telescope where it was found. These are 2 images, and basically if you blink back and forth, you can see the little dot move, and that is a moon moving around Saturn. So the 20 new moons are broken into 3 different groups. There is one prograde moon in what's referred to as the Gallic group, and this has to do with kinematics, but then they all have names, and we'll come to that in a second. So the Gallic group has 1 new moon. There are 2 prograde moons in the Inuit group, and there are 17 retrograde moons as part of the Norse group. So these are the 20 new moons. One of the retrogrades moons is actually prograde, but in the retrograde, so it looks like it's going to get smashed up just a bit on its trip around Saturn. But the fun part, and part we wanted to make sure you knew, is that you too can name a Saturn moon. So if you go to Saturn Lunacy is his Twitter handle for Scott, pardon me, Scott Shepard, who is the discoverer, and also at Carnegie Science here in Southern California. Come up with a name. My favorite part is videos, artwork, strongly encouraged. So and you don't have to be a child. You could be an adult and submit. So in fact, I think we're thinking about submitting. We've got an idea of what we might do. But name a moon of Saturn, you might win, and then you'd know for the rest of your life that you would name a moon on Saturn. How great is that?
Can I name it Noodles?
Sure. Well, I don't know. Is it a Norse, Gallic, or Inuit name? Yes, those well-known Inuit monster noodles. So they have to be giants or monsters, though, so that kind of narrows it. All the rules are in that description, and you will see it when you take a look. All right. So by way of introducing our guest, and especially for those of you who were here a couple of months ago when we had that wonderful presentation from Eric Smith about Webb, you know that there are so many telescopes in the sky. I love this photograph. Image. I had to show it again because it's such a mashup. But in fact, they aren't all spatially sitting together like that, nor even in terms of kind of the way they're managed in NASA headquarters. Today we're going to focus on the flagship missions, the big ones, and those are things like Hubble, Voyager, Cassini, that sort of thing. In other words, the expensive ones, the really big ones. And in astronomy, those flagship missions were referred to as the great observatories, from gamma rays, X-rays, ultraviolet, optical, infrared. Isn't Chandra? Well, we'll just move right on then. So Compton is retired. I'm not even going there. And Hubble, thank you, Jeff, is of course still working. Spitzer is about to be retired, and Chandra is still working. So they're retiring Spitzer, as I mentioned. In January, we will be having a very special all Spitzer considered. That is January 17th. So I was saying earlier, not the first Friday, but Michael Werner, who is from the Spitzer mission, has written a book. We're going to hear all about Spitzer as they get ready to close it down in January, and a book signing. And so it'll be an all Spitzer considered, because it really will focus on Spitzer. But that's January, and tonight's November. And tonight's guest is Pat Slane, because we're here to celebrate Chandra. So let's welcome to the stage Dr. Pat Slane. And I believe we should make the switch over to your computer, Matthew and folks in the back. So first of all, let me just say, because I love this, he was my lab partner in grad school many, many years ago. But things don't change that much. It does sort of seem like yesterday. And so it's really a delight to have you back here after so many decades.
Back is the wrong word, because it's the first time I've ever been here. But
That's true.
It's great. It's great to be here in the lab together again. Well, thanks a lot. As I said, it's the first time I've ever been here to Griffith. It's really very cool. I'm here to tell you a little bit about the Chandra X-ray Observatory, which is celebrating its 20th anniversary. That's what it really looks like. And so let me tell you a little bit about what Chandra is, and then give you some very quick highlights of what has gone on in the first 20 years that we've operated the mission. To start with, as Laura said, we have a number of great flagship missions flown by NASA that are referred to as the Great Observatories. They started back, the concepts of them started back when we were in graduate school, actually. And Hubble is one that you all know and have heard of a lot. It is still operating. The other four, the Compton Gamma Ray Observatory on the left there, is not operating anymore. That operated for a while and then re-entered the atmosphere. Spitzer you've just heard about and we'll hear more about, and then Chandra. Chandra, well, let me point to the little temperature scale on this plot. Gives a basic idea of where these things operate in terms of the energetics of the things that we're looking at. So Spitzer looks at things that tends to be cooler, dust, cooler stars, etc. And then as you go up in energy and temperature, the emission from the objects moves up higher in the energy scale of the electromagnetic spectrum, up towards the X-rays. And so Chandra operates in that X-ray band. And you might ask why we would look there. Well, as I'll get to as we're going through things, there's a wide variety of things that emit in X-rays, particularly things that are exceedingly hot, exceedingly energetic, explosive, and some of those things can only be seen in X-rays. And there's a little list of things there that we can look at, including ultra-high density objects like neutron stars, energetic jets coming from black holes and such, but also more common things, including the comet that you just heard about coming to us from outside the solar system, which Chandra's going to look at in December.
Oh, very cool.
Yeah. An important thing to know about Chandra and X-ray astronomy in general is that it's not a very old field, and the reason it's not a very old field is that it couldn't happen until we could go into space. The plot that's shown here is an indication of how far down through the atmosphere towards the Earth radiation across the magnetic spectrum can reach. So in the visible range, which you can see in the yellow and green and blue lines, of course, the radiation reaches us all the way down to the Earth. Similarly with long wavelengths in the radio band, but you can see over to the right where the X-ray band resides that the radiation does not penetrate very far down. It gets absorbed in our atmosphere. So unless you can put something up to around 200 kilometers above the surface of the Earth, you're not going to be able to see the X-rays from something coming from out in space. So we couldn't do that until we could actually launch things up on rockets. That means that the field was only invented in the early 1960s. And in fact, the way it was done was that Riccardo Giacconi here, another Nobel laureate in physics, took 3 Geiger counters that are sensitive to radiation, put them together in kind of a group like this. They rotated around. They launched them up on a rocket that went up to about 285 kilometers, something like that. Stayed up for a total of about 6 minutes. They were looking to see if they would see any X-rays from the moon, actually. And the plot that you see on the lower left is a plot of what these counters saw as they were rotating around across the sky. And you can see that there's a big peak in one direction. There's a little blip there, that's the moon, they did see it. And then there's that broad, bright region in the south-southwest, which is in the direction of the constellation Scorpius. This was the first X-ray source ever discovered in the constellation Scorpius, so it's called SCOX-1. And we now know that it's actually a binary system with a normal star whose material is falling onto a ultra-compact neutron star. And that matter, as it's falling in, is getting very, very hot and glowing in X-rays, and that's why we can see it. It's a very, very bright X-ray source. This happened in 1962. You can see the publication date, December 1st, 1962. Upon the discovery of this, Riccardo Giacconi and his colleagues went to NASA and said, we needs to have, 1963 proposal, we needs to have a 12, did it say 12 feet? A 4-meter telescope. We need a giant X-ray telescope that's 30 feet long. We got to mount this thing into a rocket and get up into space so that we can have a gigantic X-ray observatory to look for more of these things. Now, this is audacious. This is like your kid coming in from the backyard and saying, I found a bunny. I put it around a blanket. I put a lamp on it. We're studying how it's interacting. We need the San Diego Zoo. NASA said no. They gave some smaller and very important X-ray observatories that were funded and that did fly. They went back in 1976 and put together another proposal that said we want a 1.2 meter X-ray telescope to fly into space. The general diagram looked sort of like this. And if you compare it to their original proposal, it looks awfully similar. The same big mirrors separated by 10 meters from a set of instruments in the back side. And that is a schematic of Chandra. So that's actually how it came about. The very interesting part about how Chandra operates has to do with its mirrors. Photons that come into a mirror the way a normal telescope would see them don't actually reflect well. In X-rays, they have to glance off of the surface of the mirror. If they come straight in flat to the surface, they just get absorbed. They have to glance off like a stone skipping off of water. And so we build these shells of telescopes, these cylindrical type mirrors, and the X-rays glance off of them and then bounce way back to a camera in the back area. I didn't think to bring this, but an interesting thing about these is that because the mirrors are essentially shaped like cones like this so that the X-rays can skip off of them. If I point that telescope at you, you can all see that it's got a giant hole in the middle. Most of the area is actually empty. And so you fill it up by putting, nesting more smaller telescopes inside. Chandra has 4 such mirrors. That's a difficult thing to do to get those mirrors to focus X-rays. It's hard to keep those shells held in a very, very firm manner so that they will create a good image. The surfaces also have to be extremely smooth because when a surface is rough, it will scatter the light. And the surface has to be smooth, sort of on a scale of the wavelength of the light. So Chandra, to have exquisite quality mirrors, had to be polished to a quality where the roughness was small on the scale of X-ray photons, which is only angstroms in size. And
just for comparison, can you tell me what else is angstroms in size?
The other thing that is angstroms in size is atoms. And so it has to be polished to a point where it's not really bumpy on too much more than the atomic level. A bit more, but not much more. Now, how do you do that? Well, you get you get a big cylinder of glass and you take some of the glass off the outside so it's not so heavy. But then you start polishing the inside to an extremely high quality. And the process consists of, as my colleague Andy St. Georgi explained to me one time, you polish it until you run out of money. And, then you coat the inside of it with a precious metal. We used iridium for Chandra, which helps reflect the X-rays better. We mount those mirrors. We put them into a spacecraft. So this here is the spacecraft and it holds the mirrors. Way on the other side is where the cameras that can detect X-rays go. The big long thing in between is just the bench that holds them apart. We strap a rocket onto the, I'm looking this way, we strap a rocket onto the backside for reasons I'll explain in a minute, load it into the space shuttle bay. It's the longest telescope that's longest anything that's ever gone up in the space shuttle. And then
30 seconds.
It was launched.
And then pray.
And then you hope it all goes well. It was launched on the Space Shuttle Columbia, which was the first one that was ever commanded by a woman astronaut, Eileen Collins.
12,
it was
11,
deployed into
10,
space.
9, 8,
I'll pause.
7, 6, 5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Houston, Columbia is in the roll. We've got a fuel cell PH number 1.
Roger roll, Columbia, we're looking in.
Nighttime
And then
launch,
after
I
that,
see.
so it was a nighttime launch. It was really spectacular. 2 other interesting things about it. It was deployed by Katie Coleman. So another reason that we have women in STEM posters up here, because Chandra was delivered by by Eileen Collins and gently nudged out the door by Katie Coleman. Another interesting thing is you may have heard right after the launch that Eileen said something about fuel cells, something or other, and people on the ground said, Roger, we're hearing about that. Right after the launch, right when you heard that, the panel turned all red in the space shuttle because there were several anomalies. It all sorted itself out within 15 seconds, maybe faster than that. So nothing was wrong, but totally impressive to listen to them under that action. So this is what happens with Chandra. That it gets pushed out of the shuttle bay. As I said, it had a big rocket on the back. They back away from it and then fire that rocket, and that sends it into a very highly elliptical orbit. It's in an orbit that, at its largest distance, takes it about 140,000 kilometers from the surface of the Earth, which, for reference, is about a third of the distance to the moon. It goes around in about 64 hours. And we take data with Chandra. It's very far away, so to get the data back, we have to use very, very large antennas on the ground to capture it. We send the data to the Deep Space Network, which is an array of big radio telescopes that are used for interplanetary probes and other things. There's a series of 3 of them around the globe. This one is in Goldstone, California. There's also a set in Madrid and some in Australia. The data come from there immediately to our operations center that we operate in Cambridge, Massachusetts, where we confirm that everything is okay with the spacecraft that we just got the data from, check everything out, and then send commands back up to tell it what to do next. Okay? So that's how it all works. Now, some highlights about things that we have studied with Chandra. This, of course, is something that you're all familiar with, the Orion Nebula. That star there, Betelgeuse, is a red supergiant star. I'll get to that. But what's important to begin with here is this fuzzy part that you're probably all familiar with. Those who aren't familiar with it, that's the Orion Nebula. It's a nursery of very young stars. This is a zoomed-in picture taken from Hubble. It shows stars being formed and newly formed stars, all in the molecular cloud and dust that is collapsing to form these stars. And those young stars produce X-rays. This is an image from the ROSAT high-resolution imager, the highest quality X-ray image that was available before Chandra. And you can see that there's a lot of X-ray emission that coincides with that central set of stars and regions around it. You can also see that there's a lot of fuzziness that you're not exactly sure what's going on. This is what we see when we look at it with Chandra. We resolve it into many, many individual stars. A very important thing about Chandra, other than that very high resolution optics that I mentioned to you, and for numbers that we always have to throw out, the resolution of Chandra is such that it could resolve the size of a dime from about 5 miles away, something like that. An additional very important point is that when we take pictures of it, not only do we get pictures with fine, very fine spatial dots around them, but we also get the energy of each one of the X-rays that comes in. And so we can differentiate things that are primarily high energy X-rays, primarily low energy X-rays. In this picture, we've taken low energy X-rays and colored them red. Medium energy ones green and high energy ones blue. And so you can see that we have some stars that are reddish, they're cooler stars, some that are medium energies in the green, and some of them that are blue that are either really hot or they're absorbed, that they have a spectrum where the low energy X-rays have been absorbed out. We can study more than just the newly formed young stars. I mentioned Betelgeuse before, which is a star that's towards the end of its life. It's an older star that is expanding and cooling. Its outer layers are turning red. But what we know about stellar evolution is that what's happening in the center is it's running out of nuclear fuel. You heard a little bit about the nuclear fuel process in stars before. It's running out, and like all very massive stars, it will eventually burn through its hydrogen and helium that it's fusing. The core will collapse until it gets hotter, and it will fuse heavier elements until it's filled with a gas of pure iron. At that point, it can't generate any more energy through fusion to hold off the gravity. And so the core of the star simply collapses in order of a couple seconds through very interesting physics that ultimately results in an explosion, leaving an outgoing blast wave that goes out into the interstellar medium and a compact core where the core of the star collapsed. This is all just an illustration, and I've tried to mark everything here tonight that is an illustration and not a real image with a note that says illustration. This is not an illustration. This is the first image release from Chandra. It's the supernova remnant Cassiopeia A. It's from a massive star that exploded in the late 1600s. We knew about Cassiopeia A before. What's interesting from the Chandra observation, there's a couple things. One of them is that you can see a lot of fine structure that we were never able to see in X-rays before. These stars, when they blow up and they expel their innards out into space, have material flowing out at tens of thousands of kilometers a second. And that gets very, very, very hot. So it generates a lot of X-rays. We see Cassiopeia A here and other supernova remnants like it more in X-rays than we do in any other wavelength band. The other thing that's important about this is the little, can I point to it? I probably don't have to, but the little point right in the center. That hadn't been seen before we pointed Chandra at it. Because the other telescopes didn't have fine enough resolution to see it. That is the neutron star that core collapsed into when Cassiopeia A formed. Now, yes, neutron star. Now, as I mentioned, an interesting thing, an important thing about the way Chandra works is that we can measure the energy of the X-rays that come in, okay? And this is a plot showing you how many X-rays there are that are of high energy and low energy and medium energy. So going from left to right, left is low energy, middle is high, medium, and right is high. The units that we use here don't matter that much. What you just need to know is that it's getting higher as you go to the right. And so if you look at this plot, there's a lot of X-rays at an energy of about 1 in these units. There's even more at an energy of about a little under 2. And then as you get to really high ones, there's not as many high energy X-rays. The bumps and wiggles that you see in here are very important. They correspond to X-ray emission from very specific transitions from silicon, sulfur, argon, from discrete atoms. And so they allow us to see how much of those materials are in these explosions. Now, in these massive stars that explode, you know, as I was saying before, that elements are fused in the center of the star. Laura mentioned before that in the early universe there was primarily hydrogen and helium because nature is lazy and it just makes one proton and one electron. And every once in a while, 2 protons, 2 exactly. But it lets gravity collapse stars and generate much heavier elements. When they get generated, they get expelled into space in these supernova explosions. And I mean, it's kind of important because to begin with, there isn't a whole lot of some of these key elements. Like you can see to the left there's a little bump from oxygen, okay? There's 4 things on this plot that are like crucial for life as we know it. There's oxygen that we breathe. There is iron, the iron that is in our blood. There's the calcium in our bones. And the silicon that makes the computer chips that make our cell phones work. You can do something interesting by asking where that stuff is in Cassiopeia A. We can look at this and say, let's take the X-rays that are in the around 1 unit of energy, which comes primarily from iron. There's a little bit of iron and oxygen, neon and oxygen in there as well, but mostly iron. let's look at silicon and color it red, sulfur, yellow, calcium green, and the highest energy stuff blue, okay? And when we do that, we can then make pictures of Cassiopeia A in those different elements, and you can see that they're not all distributed the same way. In the explosion that happened here, the different elements that were formed got redistributed in very complicated ways. We can put those all together to form what Cassiopeia is really showing us in terms of the structure of this stellar explosion. And we can, yeah, so I better hold off. We can also look at individual pieces of Cassiopeia, look at the spectrum, and see if those lines, those peaks that I showed you from silicon and from calcium, if they are shifted away from where we think they should be in energy. If they are moving, if the material is moving towards us, it will be blue shifted towards higher energies. If it's moving away from us, it'll be red shifted towards lower energies. And that means that we can actually make a three-dimensional model of Cassiopeia A by looking at where the stuff is in the picture and how it's moving backwards or forwards. And so this thing that I'm showing on the right is a combination of not only Chandra data, but other data where the same trick was used. And this is what Cassiopeia A actually looks like. These explosions are anything but spherical bombs. They're very, very complicated. Going away from individual stars, but to larger scales in the universe, you know this as the Milky Way. This is a Chandra image of the center of the Milky Way galaxy. At its very center is a supermassive black hole called Sagittarius A star. And that's shown in this X-ray image. The plane of the galaxy is that line, just giving you some orientation here. And what's interesting is that the black hole in our galaxy, it's about 4.5 million times the mass of the sun, is kind of wimpy as far as black holes in centers of galaxies go, okay? And it's kind of active. It's kind of glowing because matter is falling in on it. What you see in that graph up on the right is a plot of the X-ray emission coming from it, and you see every once in a while there are some spikes in it, because every once in a while excess material falls into this black hole and it generates these big flares. And the inset image there is kind of showing that. It's showing a movie of the Sagittarius A star from Chandra, and every once in a while it gets brighter. But overall, it's really not very active compared to some other black holes, as I'll show you. However, at some time in the past, it probably has been, because you notice in that image that there are those red-ish lobes of energetic hot gas that must have been thrown off in earlier and more explosive episodes. That does happen in other systems. This is an elliptical galaxy called M87 in a nearby cluster of galaxies. Its central black hole has about 6 billion solar masses. And when you zoom in on it in the optical, if I can do this without getting dizzy, you can see a really bright jet from activity from the central black hole. Materials falling onto the central black hole, creating these giant outbursts and creating a jet of material that's coming out of it, okay? You all know about M87, or some of you do, probably most of you do, because this is the one for which earlier in the year, the Event Horizon Telescope actually released an image that shows the shadow of the black hole that is at the center of this galaxy. Now, you might ask yourself, what should the impact be of these giant explosive events coming out of these black holes, okay? I mean, what we have here is there's sort of like a giant atmosphere of gas around that central black hole. That's what that blob is there. And you're shooting jets of material out into that atmosphere. What would that look like? Something like this, okay? You shoot out this jet of energy. It floats buoyantly out into the atmosphere, and it raises up and creates this sort of a smoke ring. If we look at M87 with Chandra on a backed off scale, where we've blurred in the jet and things in the very bright middle there, you see these outskirts regions with these big loop-like structures where there have undoubtedly been, apparently been, big outbursts from the black hole that have blown these big cavities out into the surroundings. And in fact, if your eyes or imagination are good, you can perhaps see right where that big circle is that I'm blinking on and off, that it's bright inside of it and it falls off just outside of it. That's a shock wave where 12 million years ago, based on calculations from the analyzing the Chandra data, there was a massive outburst that, okay, what was the number I calculated before I came in? It was several trillion, billion megaton bombs of energy per second on the average. Massive events from things falling into black holes. Going out a little farther than that, and a slide that's very similar to, but not identical numbers to what Laura was showing before, I guess within round-off, they're all the same. This is what we think this is what cosmology currently tells us the universe consists of. There's the 4% normal matter that we're all made out of. There's the 21% dark matter that we know is there because we can see it acting gravitationally on stuff, but we can't see it. Hence it's dark. And then there's this 75% that's dark energy, which is a sort of an overall pressure in the universe that we're just really coming to learn about. What can Chandra tell us about that? Well, this is an image that shows a cluster of galaxies. Almost all of the little points that you see in this image are actually individual galaxies. And these galaxies gravitationally cluster together as the universe evolves. To begin with, they're not clusters at all. Galaxies form, then they cluster together, then more galaxies merge and form bigger structures. This is what it looks like in the visible light. If we look at this with Chandra, this is what we see. The material in between the galaxies is filled with million-degree gas. Diffuse gas that's been stripped off the individual galaxies, heated to very, very high temperatures, and it just glows in X-rays. That represents a lot of mass, mass that you can't see if you don't look at this in X-rays. There's no other way to detect that. But what's also interesting is the structure of this, right? The thing on the right kind of looks like the bow of a boat going through the water. And that's exactly what's happening here. We have two clusters of galaxies. They're merging through one another supersonically. And the thing that you see on the left is like a bullet moving through the air. It's forming a bow shock, and this is referred to as the bullet cluster. This technique of finding clusters of galaxies from their X-ray emission is something that Chandra is able to do all over the universe. So we look at this beautiful bullet cluster, but we've taken images of many, many, many different clusters and made measurements of their temperatures and their sizes. And that allows us to probe structures of the universe in the following way. When the universe first formed, as I said, and as an early slide that Laura showed, the material was all far apart, and eventually it coalesced into these galaxies. Well, it wasn't far apart, it just didn't coalesce into structures. Then eventually it coalesced into structures. If we look nearby, we can ask ourselves, okay, how many big clusters of galaxies should there be? How many small clusters of galaxies should there be as these things all sort of fall together? And this plot here shows small clusters to the left, large clusters to the right, and the number of them. That's what that plot shows. So there's not very many large clusters. There's a lot of small clusters. And as time goes on, you get more and more of the large ones. Now you might ask what things look like at the earlier part of the universe, which we can find out by looking farther away. We can look at clusters that are more distant and say, how many big ones were there? How many small ones were there? did the universe coalesce the way that our physics would suggest that it should have. This plot that's got that red circle around something that says omega lambda equals 0, okay? But as Laura explained, lambda is just the indicator for dark energy, so I don't have to explain that anymore because it's all clear, right? This is a model where there is no dark energy, and it's made to fit our data on clusters that are close to us, okay? This is what it would predict for the number of large and small clusters that are much farther away. And this is what we actually observe with Chandra.
Oh, isn't that great?
Okay? Yeah. And so what it's telling us is that we really don't have, at large distances, we really don't have as many large clusters as we thought we should. Now, why not? Well, because there's dark energy that is providing another pressure support that we weren't thinking about, and it's kind of holding them off from coalescing together. If instead of having no dark energy, we say, yeah, let's suppose 75% of the matter energy density is in the form of dark energy, then we get this. So this is a completely independent way of demonstrating not only the existence, but actually the quantity of dark energy in the universe.
I just have to say that's so elegant and lovely to just see that, because now everything, I mean, there are so many observational posts that everything has to hitch to.
Right.
And so you'd think, well, this is also crazy and it's also theoretical and there are these computers doing these models and how do you ever really know? But the fact is you have to match all of these observational posts.
Yeah.
And it's a really lovely
And when people
example.
did it with supernovae,
Yeah.
it was like, okay, wait, are they doing something
Yeah,
wrong? Is there
right.
This is just a completely different
Yeah.
way of doing it and getting the same result. So lastly, to move much back closer to home, there's this Chandra observation. Does anybody want to guess?
Pumpkin.
Pumpkin. That's not even close.
I was just trying to help.
Oh, look at that.
Who?
Jupiter.
Oh,
Yeah.
good one.
Did anybody in here? I know somebody in here. Did anybody in here go to the 5:15 planetarium show? Okay. So, what's going on here? That's right. What we have here is the equivalent.
It's the Vikings and the,
It's the Vikings.
and the Valkyries. Is
That's
what's
right.
going on there.
Well, what's going on here is that Jupiter has a magnetic field. The sun has a solar wind of energetic charged particles that's going out into the solar system. Some of those are being funneled down to the poles of Jupiter, exciting the gas there and generating X-rays. Just like we see, I forgot to check if this slide actually works. Yes, just like we see here on the Earth. These are aurora pictures that my wife and I took in, I forget, 2 years ago? 2 years, in Iceland anyway. So Chandra studies things from near to far. It studies very energetic objects from explosions. It studies very energetic objects from objects that are just very, very hot. And it's been going on for 20 years, and we are currently funded for another 10 years of operation from NASA. And
That's great.
So we're looking forward to a lot more of this. And
Is there less than a pound of iridium in that telescope?
less than a pound of iridium. It's a good question, and I should know because I did the studies about what we should coat it with, but a pound. I'm going to guess that there's definitely less than a pound, but I would have to do the calculation to be sure. But you can, the mirrors are, the outer mirrors are about 1.2 meters in diameter and also about 1.2 meters long. It's the inside of a cylinder, and it is 400 angstroms thick. So you can go and calculate that. I don't know the answer off the top of my head, but I would say it's less than a pound. I'd be surprised if it was more. Yeah.
Yeah.
So that's all I have for you.
Well, thank you so much, Pat. we have a couple of minutes for questions. Well, we don't, but I don't care because all the timing is, and this is a small group anyway, and so I think we can kind of throw the schedule out the window and do what we want. I'm happy to skip all of my talks except Alexei Leonov later. Are there questions for Pat? Yes.
Yeah, I'm puzzled by the these flares that occur, or any kind of matter, or energy of matter that seems to be ejected when you have these from the black holes. Because isn't the gravitational pull of a black hole so great that nothing can be ejected from a black hole?
Yeah, that's a good question, and one that is that's asked a lot actually, because we oversimplify these things. The material is falling into the black hole, but before it crosses that event horizon of the never to return, it gets so hot that you get these explosive events. So the explosive events are happening outside the event horizon. They're happening because of the ultra high gravity, but the material itself is still well outside of that never to return point. I will say, though, that you can see the effects of it. If you look at the spectra of those things, the spectra are shifted towards different wavelengths that has to do with being in a very, very high gravitational field. So when you study the spectra from those flares, you can get a very good measure of the gravitational field from those shifts.
While others are thinking their question, I'm going to take and ask you, what's this? That was just released. Can you tell us a little bit about it?
This is this is a recent image released from Chandra, and this is a mosaic. Really, the background is optical image of a cluster of galaxies, and what it's the gravity of that cluster of galaxies is acting on light coming from behind it in such a way that it is the gravitational field of the cluster bends the light and makes it form sort of a lens, and that's what's forming those arc-like structures. The purple is that hot gas in clusters that I was mentioning before. That's the X-rays tracing out where this very, very hot gas is. And so as I said before, you'd look at this before, if you turn the X-rays off, you'd see all of these galaxies, but why is that lensing looking the way it does? Where is the mass? Well, the X-rays are showing you where the mass is. It's not showing you all the mass because most of it is dark matter, but the X-rays are following the dark matter and they're showing you where that gravitational lens is sitting.
So I remember the Hubble image, of course, but it looks like that image got a spray tan. So that looks to me. Are there any other questions? Yes.
I have a question on as far as the dark matter versus dark energy. Other than calculating it to exist, how do we observe it if it's unobservable?
Well, that's a very, very difficult. Well, it's a difficult question, but it's also a difficult thing to do. The dark matter we can observe in the sense that we see its gravitational effects, right? We can look at a galaxy, we can see its structure and calculate from the points of light that we see in it how much mass has to be there. Then we can also add up all the light we can see, and we can say, I know that on the average stars are this bright, so stars of this mass are this bright. I can add that all up and get the mass. And it's not nearly enough to explain how the whole thing is bound. So that is mapping or measuring the dark matter. It's not seeing radiation from it because it doesn't seem to radiate in ways that we're able to observe. Dark energy, again, the only thing we can see from it is its effects. We know the universe is expanding. We know that there's a bunch of gravity, so that expansion should, in principle, be slowing down. It's not.
So it's something that we can deduce but not observe yet.
You can observe the effects, but not the
directly
stuff.
observe the stuff.
Yeah,
Not
you watch
directly
the
observe-
stuff
that's
having
right.
an effect on
That's-
the normal matter around it.
Yeah, so if I'm going to the store and I want a jar of dark matter, that's going to be kind of hard to get.
That is going to be hard to get.
Make a lot of money bottling that. We could just have a jar. It's a jar of dark.
That's and it's heavy.
Yeah, right. Question in the back corner.
Quick question. So, since our universe is expanding and accelerating, does it accelerate at the same or similar rate? And if not, do you know why?
Do you mean, does it accelerate at the same rate everywhere?
Yeah, everywhere, all the galaxies.
Yes,
Go
I
ahead.
think what you're getting at is it's universal from what we observe. It's not like this part of it here. Once you take out the local attractions of gravity, the universe as a whole is going through a uniform experience of this dark energy, is I think the best way to say it.
Right.
And moreover, it does appear to, although it's changing the expansion rate, they refer to it as a well described by a constant, which is that lambda cosmological constant. So
except
we're
for on
still
small
learning
scales,
about
but
it. Yeah,
yes.
yeah. But as
as
the
a whole,
overall,
that's exactly right.
So it strikes me that we could turn this into a cosmology 101, which I would love because I'm really excited about it. But I fear that would not permit us to get to some of the other stuff. So general cosmology questions, I would love to do just a class or a lecture next year that's about that. Would you come? Would you want to? Okay.
There you go.
We're going to do that. We're going to do that.
Question.
Yes, last
I
question.
read that there's a mirror universe that we haven't discovered yet. Could a portion of the dark matter be antimatter?
No, not as we know it, because we would know the signatures from antimatter. If there is another such universe, it may have the imbalance of matter. We have an imbalance of matter to antimatter. It might have the flip-flop, but
And it has evil Pat Slane.
no, this one has evil.
Oh, that's a good place to end. So I'm going to skip through. We're going to have a little chance at break for those who have individual questions, but I want to just get through to our last little bit. So I'm skipping through several Chandra pictures that we had, but we do want you to look up in the month of November because there's so much to see. So Patrick, can you tell us what's in the sky for the month of November?
Okay, yes, and the first thing you must do this weekend, and we go to the next slide, is to set your clocks back. The clocks are going back 1 hour at 2 a.m. on Sunday.
So I'm going to interrupt just
Go
to
ahead.
say that, we were looking for graphics, and these are all these lovely ones, fallback. So, but as you know, we have this wonderful staff that helps us put the show together. So we asked them, could you put together our own original fallback? And this is what they came up with. So that's fall back. So you can think about that Sunday morning when you get up.
So I second that, the same message. Okay, so if you're, being that we're going to go back 1 hour, that means that you can go out earlier because it gets dark earlier to observe the sky. So in the last few days, we've been watching with interest the emergence of Venus. You can see it's marked there. I took this picture on the 29th, and there's a nice one-day-old moon just above Venus. And then just a little bit higher up is the planet Jupiter. Those 3 planets will be visible soon after sunset. We have a little close-up picture of the two. It's, makes for a nice photogenic view. So if you happen to go out, take a picture of it. You can. When it gets darker, you might be able to see Saturn. So there's a lineup on the 5th, Venus, Jupiter, Saturn, and then the waxing gibbous moon a little bit higher up. But 18 days later, Venus and Jupiter will be close together in the sky, just separated by 3 moon diameters. And this is definitely something that you want to go out in the evening to look at and take your cameras to photograph. I certainly will be out there watching for this. And take a look at the next day too, because you can see the relative motion of Venus to Jupiter. And the two are not actually in the same, I mean, they are, Jupiter's 500 million miles away, and Venus is 136 million miles away. So it's just a line of sight that you're seeing here.
The Great Conjunction is the end of the world! Oh, the beginning?
And they just said it. That operative word is conjunction, when two planets are close together in the sky. So if you want to do some stargazing here, we mentioned earlier, in fact, David did, the constellation Pegasus. And we'll put the lines up here because you can see them here. The square of Pegasus is made out of 4 stars. And this is the overhead position, so you have to look straight up in the middle of the month. And it's connected to a constellation called Andromeda, and this little offshoot here is M31, or the Andromeda Galaxy, which you can see in a dark sky with your eyes. It's the farthest spiral galaxy you can actually see with your eyes. And in a pair of binoculars, it looks like an elongated fuzzy smudge. Now, in the beginning, actually, the 2 stars in the front of Pegasus, this one and this one, you can use as pointers, and you can find this lonely first magnitude star called Fomalhaut in the southern fissures in the south there. Over to the east, the red star Aldebaran is above the horizon, and the constellation of Orion is just emerging. Just a few days ago, I took this picture, and you can clearly see Orion rising there. There's M42, as Pat was saying, which is the Orion Nebula. And so go out and look for that in the late evening. And how are our moon phases doing this month? Well, they've all turned into pumpkins. So one thing you might be interested in is on the 2nd, we have a star party here at Griffith Observatory where local astronomy clubs come up, set their telescopes on the lawn, and you can look through telescopes at Jupiter or even Venus or any other celestial object they will be showing that night. So it's worth a treat. So if you're coming out here, you might want to do that. The full moon, is on the 12th. And if you're up early in the morning on Thanksgiving morning, which is on the 28th, you're going to see the Big Dipper, which is high overhead, and you can use the 2 stars to point in the front of the Big Dipper to point to the North Star. And you can use the handle and kind of form an arc towards this orange star called Arcturus, and then you can speed down to Spica, which is in the constellation of Virgo. Constellation of Leo is a backwards question mark, and a triangle. The bright star is called Regulus. So if you're up early that morning, do take a look in the morning sky. Now, something that is a rare event that's coming up is Mercury. Mercury will be passing directly in front of the Sun on November 11th, Veterans Day. And when it does this, we call it a transit. And at sunrise, which is 6:22 from Los Angeles, the transit will already be in progress. So Mercury will already be kind of somewhere over here. And at 7 a.m., it's going to be here. 8 a.m., it's going to be here. And then it'll take 4 hours to reach the west limb of the Sun at 10:04, and then the transit ends. Now, the last time we had a transit here in Los Angeles of Mercury, it was clouded out, May 9th, 2016. But we did get eventually, when the marine layer kind of started thinning out, a glimpse of the Sun. But as in every, because of the transit, looking at a transit of the Sun, when I say look, you should, I actually want to emphasize that anything involving an observation of the Sun, we have to give you a note of caution here. And so this next slide is just to remind everyone, never ever under any circumstances look directly or stare directly at the Sun for an astronomical event, because it could mean that will be the last astronomical event you'll ever see. And and so by mean everyone, that includes everyone. Oh, the eclipse sunglasses? Well, the thing is that the Mercury is going to be about 0.5% of the total diameter of the Sun. It's going to be a tiny speck. It's going to be very difficult to see. So we'll have, in order to see it properly, you need properly filtered telescopes, and to actually get a decent image of Mercury crossing the face of the sun. In fact, the best way to see this, and I'm going to recommend our website here, because we're going to run a broadcast from our telescope on the roof with, of course, it's going to be all properly filtered light from the sun, and we're going to broadcast on YouTube and live stream the transit starting at 6:15. So if you want to tune in for that in that morning, tune in just before 6:15, and you can look at it from our website here at YouTube or a live stream.
Let me just say that we did do this before, and so the video we're about to show will show you what we got before, but bear in mind those cloudy clouds we had. So you can see the little dot. There's not much to show you there. We didn't have, it was cloudy. So I'm going to run through that again just so you can see it. But you can see Mercury, which is a thing. And it's Mercury.
So there are two more transits, but they occur on the other side of the world, not visible in North America. But the next one, you have to wait to May 7th, 2049. So catch this one on our live web broadcast if you want to see it.
And there are a lot of things happening in November, so you'll want to tune in to see the Mercury transit. You will also want to tune in, or better yet, come here on the 16th of November when we are celebrating Apollo 12 and the 50th anniversary of Apollo 12. It's a Saturday. There will be a series of short talks, that'll be roughly 20-25 minutes, and then we'll have our All Space Considered Remembers Apollo 12, which will be about a 50-minute talk. You can see the times. It's all on our website. There will be activities on the lawn. It's good for families. So come celebrate Apollo 12 for us. And then, as already mentioned, in January, come back for All Spitzer Considered. So this next story, we're going to just show a couple quick pictures because it's just something that was fun to see here. That Patrick,
right.
who are these?
So, yeah.
Who are these people, and where are they from?
This is a flyover over the observatory by the Royal Air Force, who were on tour back in beginning of October. This is Britain's aerobatic display team, and they did a flyover Los Angeles for publicity purposes. And we were surprised to get a nice view of this, and especially the people on the lawn.
So quite a fun sight.
Yep.
And then we had a story that I'm not going to take any time to tell you about zebras. Because you think zebras look like that, but who knew cows look like that? And that's because they painted this cow to see whether or not the cow got bit less, because that's the idea that was postulated was the stripes help zebras get bit by flies less. So they did a test that actually resulted in a scientific paper. They first did it on some barrels, but then they did it on a cow, and the answer is yes, they had half as many fly bites, as they did when they weren't painted with stripes. So it's just kind of a cool optical situation. So with that, we are about to go to Pretty Pictures, which is the end of the first half. And so we're going to say goodbye to our live stream audience and our YouTube audience. We're so glad that you joined us. And we will be posting videos from the second half on our YouTube channel, so check back over the weeks to come and you'll see segments from part 2 as well. But thank you for joining us for now, and Matthew, you can cut our transmission, and then we'll just be